Okay, to start looking at this first pattern, we want to look at the dimensions of these shapes. So in size 1, we have a width of 2 and a height of 4. Next one is 3 by 5. Size 3 is 4 by 6. Then we move to 5 by 7 and 6 by 8. So that tells me a lot. That tells me that the dimensions are actually based on which pattern I'm looking at by the sizes. For example, size 1 being 2 by 4, that lets me say that, well, I know the width is 1 larger than the size, and the height is 3 larger than the size. And then if I check that as I go through the pattern, it remains the pattern for the rest. So for size 2, the width is larger by 1, the height is larger by 3. Move to the size 3, width is 1 bigger, height is 3 bigger. So that gives me one way to write the formula. Then I can express length times width, express the area by saying that it's the size we're looking at plus 1, that's our width, and the size we're looking at plus 3, that's the height. I need one more expression. This does say select 2 expressions that will model the area. So one way I could do that is, since I'm pretty confident that this product of binomials is correct, it's size plus 1 times size plus 3, I could just FOIL that. I could say s plus 1 times s plus 3, and I can multiply those and say s times s is s squared, s times 3, 3s, 1 times s, 1s, 1 times 3 is 3. In the middle, this 3s plus 1s, those are like terms, so I combine those, get 4s. So my second correct formula would be E, the s squared plus 4s plus 3. Now, if you do not come up with that original expression, the s plus 1 times s plus 3, if you don't catch on to a pattern that you could describe that way by just looking at the pictures, then the next best thing would be count the number of little tiles or boxes that are in each pattern and make a table out of it. So we know that the size would be our independent variable. The number of tiles would be the dependent variable. So we have size 1, 2, 3, 4, and 5. So the total count, 2 by 4 would give me 8 tiles. In the size 2, 3 times 15, or 3 times 5 is 15. Size 3, I have 24, 35. And size 5 is a 6 by 8, so that's 48 tiles. Now I would have to analyze that pattern to see whether it's linear, quadratic, exponential, or none of those. This goes up from 8 to 15, goes up 7, then 9, then 11, and 13. So I noticed that that is a linear pattern, or if that doesn't set off any alarms to you, I can look at second difference. From 7 to 9 goes up 2. From 9 to 11 is up another 2, another 2. So my second difference is constant. So either one of those should be enough to tell me what I'm looking at. But one way or another, I discover, oh, this is a quadratic pattern. So if it is quadratic and I have a table of values, I could enter them in my calculator into L1 and L2, and then use the quadreg feature to come up with an equation. Now the calculator always gives you the equation in standard form. So if this is your method, you're going to get the s squared plus 4s plus 3. That would be your first formula. And then you would need to factor that to turn it into the s plus 1 times s plus 3. Okay. So how many tiles, number 2, how many tiles are needed to build stage 7? If you set up a table, like we just now did, you could just extend that 2 places and you'd get to stage 7. That would mean add 15 and then add 17. Since we have formulas, though, and we're going to assume that you're pretty confident in the formulas you chose at number 1, we would just substitute 7 in for the s or x or whatever the variable is. So let's take that formula at b, that s plus 1 times s plus 3. If I want size 7, and s is 7, I'm 7 plus 1 times 7 plus 3. That becomes 8 times 10, or 80. If you had more confidence in the standard form, we're looking at e there, s squared plus 4s plus 3. If I replace each s with 7 in this formula, that's 7 squared plus 4 times 7 plus 3, which simplified is 49 plus 28 plus 3. Well, 49 and 28 make 77, plus another 3 is also 80. Okay. Now, I've included these little calculator symbols on the side of certain questions throughout this review to indicate that if all else fails, if you are just stuck, lost, trying to guess, your calculator could help you with these by simply trial and error, by taking each of the formulas in number 1 and type those into y equals in the graphing calculator. Go look at the table and see which one matches the results that we have here, that when x is 1, y should be 8. When x is 2, y should be 15, and so on. Okay. Number 3. If we're enclosing a rectangular garden, and that's key here because we know certain properties of a rectangle, that there are 2 sides with the same length that we describe as width, and 2 sides that we describe as length, and they are equal also. Okay. Now, this one says we have to have a total of 56 feet of fencing. That is describing perimeter. Whenever you're talking about the outside of a shape, it's considered perimeter. If the perimeter has to add up to 56, that's the total of all 4 sides. And perimeter of a rectangle is going to come from 2 of the length, okay, 1, 2, plus 2 of the width, 1, 2. Those have to equal 56. But you can see none of these choices in the multiple choice over here. First, they don't even have L or W. This asks us to use X for the width, but they don't have 2 variables at all. So that means I'm going to need to relate the length and width to each other using one single variable X. All right. Well, first step in doing that is to simplify the equation I just wrote, the 2L plus 2W equals 56. All of those are even numbers, all of those coefficients. So if I divide the entire equation, both sides of that equation, by 2, it tells me that the length plus the width would have to equal 28. So now, if this question asks me to use X for the width, let me replace this W with an X. So then how long is the length? If I solve this for L, that tells me that the length would have to be 28 minus X. Okay, so I have width of X, length 28 minus X. So in order to write an expression for all of the possible areas of this rectangle, area of a rectangle is length times width, or in this case, X times 28 minus X. So that's choice C. All right, we've done a whole bunch of practice with these identifying tables as linear, quadratic, or exponential based on their first and or second differences. So just as a reminder, here's how we described what we would see in each first or second difference for linear, quadratic, and exponential. You'll need to know that. That's not something that you can ask during a test. You're supposed to remember those. So let's just go to each of these tables and do our first differences, see what it tells us. So in this table F, first differences go 3, 3, 3, and 3. That shows me that the first differences are constant, meaning this table is linear. Now, had I not known what I was looking at with all the 3s, I would do second difference and say, there's no change, that's 0. No change is 0. No change, 0. So my second difference there is 0, another indicator that this is a linear function. I look at table G, from 3 to 9 goes up 6, then it goes up 18, then it goes up 54, and lastly, that's 162. Okay, now those are kind of large numbers. They may not mean much to you. So if I look at second differences, from 6 to 18 is an increase of 12. 18 to 54 is an increase of 36. And 54 to 162 goes up 108. So in both the first and second differences here, what I see is a common ratio. So this, either the first or second difference showing a common ratio means this pattern is exponential. Now, if you have forgotten what common ratio means, in other words, it's saying that we have a multiplier. 6 times 3 is 18, times 3 is 54, times 3 is 162. We see that same pattern in the second difference is 12 times 3 is 36, times 3 is 108. We describe that as a common ratio. In the table H, we see the first difference from 5 to 13 is an increase of 8, then we increase 10, then 12, then finally 14. So that is a linear pattern as first differences. I'm already convinced this one is quadratic. However, if that doesn't scream linear to you, look at your second differences. From 8 to 10 is up 2, and another 2, 2 more. So now I see a constant second difference, which also is enough to indicate quadratic relationship. Number 5, we are talking about average rate of change, or in other words, average speed, which even though this is not a linear function, whenever we calculate average rate of change, it's really a matter of doing the slope for just the 2 points indicated. So this says we want to look at the points or the values from 1 to 4. So I'm going from the point 13 to 481. Okay. Now the slope formula is y2 minus y1 divided by x2 minus x1, or in other words, delta y over delta x. Okay, so if I subtract my two y values, 81 minus 3, and I divide that by the difference in my x values, 4 minus 1, I get 78 over 3, or reduced divided, that's 26. So my average rate of change here is 26. Okay, numbers 6 and 7 again indicate that if you get stuck and you have the time at the end of the test, you can just use your calculator, check each of those choices one at a time, try to match it to the graph you see. But hopefully we don't need that. Hopefully we can do vertex form by just identifying the vertex, in this case 6, 9, and then remembering or using your formula sheet to say, hey, vertex form looks like A times the quantity x minus h, quantity squared, plus k, where HK is the vertex. Well, if the vertex is 6, 9, I need to replace that H with a 6 and the K with a 9. So that would leave me with choice C. All right, now we did not mention that the A here was a -1. The negative sign just makes the parabola open down. That doesn't really affect the vertex. Okay, choice 7, and this is one of the newer things we've covered. This is factored form of an equation. Now, factored form is x minus d times x minus e, where d and e are the x-intercepts. So if we just go over here and identify our x-intercepts as 3 and 9, we just need to substitute those values in for d and e. So we would want x minus 3 and x minus 9. And once again, that was choice C. The negative sign in front of the first parentheses is, again, just an a value of -1, which is why our parabola is open down. Okay. For choice 8, we're referring to the same, or question 8, we're referring to the same graph. Range is y values. When you're reading the possible y values on a graph, it's represented by whatever the bottom of the graph is to the top. So this graph, if I tried to start from the bottom, these arrows here indicate that it continues down endlessly, infinitely, forever. So there is no bottom, but it does have a top right here at the vertex. So the highest y value, again, range is about y values, the maximum y value is the 9. So y can be anything lower than 9 or 9 itself. So every y value from 9 down, that would be represented by the inequality f of x, same as y, f of x is less than or equal to 9. All right, so number 9, we have both a table and a graph to represent a quadratic function. And we know most of the equation, we're only missing the a value. Now remember, a controls two aspects of the graph. If a is positive, it's open up. If a is negative, it's open down. But a also controls the steepness or the width of the parabola. So when the absolute value of a is greater than 1, it gets steeper. And if the absolute value of a is between 0 and 1, it gets narrower. I'm sorry, wider. The steeper is actually another way to say narrower. So I like to look at the graph to determine the a value. I know it's going to be positive because it's open up. So I can immediately eliminate this negative choice. It's definitely a positive value. It's hard to tell with this graph if it really was any narrower or wider than the parent graph. So what we do is identify your vertex, and if you look one place to the left or right and determine how far you have to move either up or down to get to a point, that is your a value. So what I'm seeing here, when I go either left or right one place, I need to go up not even one whole unit. It looks like it goes up 1/2. Now, to be certain that it really is 1/2, I need to use this table over here. So the vertex is at 3, -1. That's the first point here in the table. And I don't have the values that come before 3, so I can't really use this point, but I can use that point 4, -1/2. Since the point right next to the vertex, 3, -1, is 4, -1/2, that tells me it went up exactly 1/2. So your a value is exactly 1/2. choice C. Now, another way to find that A value is A is always half the second difference. So with this table of values, you could always come over here and do your first differences from -1 to -1/2 up a half. Next one goes up 1.5. Next one goes up 2.5. Next one goes up 3.5. So my second differences would be up 1, up 1, up 1. Half of that second difference, half of 1 is 1/2. So that is a second method to find your A value. And again, if you're desperate, you could try replacing the A in this equation with each of the values that you are given to choose from, and take them one at a time, look at the table in the calculator until you find one that matches what we're looking at here in the question. All right, so for this number 10, here we have a graph, but with no specific point values to know exactly where it was translated, how much it was dilated. So all we can do is compare each of the parameters A, H, and K to 0. Okay? Now, with the A value, we know for any quadratic, for any parabola, which is what we have in the picture here, A can never be 0, because if it were, you'd be doing 0 multiplied by your x squared term, removing the x squared, so then you'd be left with only a linear equation. So A can't be 0 for a parabola. So we're left to say, well, it's either then less than 0, a negative number, or greater than 0, a positive number. Since this parabola in the picture is open down, that means it has to be a negative value. So A must be less than 0. The H controls whether the parabola moves left or right. It's horizontal shift. So this one being still, the vertex is still on the y-axis, that means it has not shifted left or right at all. It has stayed kind of right in the middle of the graph. So H is exactly 0. All right, now for the K value, K controls the vertical shift, either up or down. Well, this vertex has shifted from the 0, 0, the origin where our parent graph rests, it has shifted down. So the only way to make the parabola shift down is with a negative K value, so K has to be less than 0. Now, the interval of the domain, so that means based on the x values, for which the f, the graph over here on the right, is decreasing. Now, one common mistake is that if people look at a parabola that is open down, they think the whole thing is decreasing because they're reading it from the vertex down, saying, hey, both of these, both sides, the left side and the right side, will continue to decrease forever. But you don't read a graph from the top to the bottom, you read from left to right. So as I look from left to right, this first side of the parabola is increasing. Once I get to the vertex, the definition of a vertex is a point where the graph changes direction. It changes from increasing to decreasing. So if I'm asked here about which side of that parabola is decreasing, it's the right side. It's over here. So that shift happens at the vertex, or in other words, it's separated by this line of symmetry. Well, with the vertex on the y-axis, my line of symmetry is x equals 0. If I want everything to the right of 0, everything after 0, that means we are decreasing when x is greater than 0, after we pass the line of symmetry. Okay, number 12, something really recent that we worked on, which is perfect square trinomials. We need this value of c that would force this to be a perfect square. Now, we had a process where we just would take the b value here, the negative 30, chop that in half, so we get negative 15, then square that result. So negative 15 squared is 225. That is the only value that will make this a perfect square. Now, you might have looked at negative 15 squared, written it down like this, and then if you type it in the calculator, it tells you that's negative 225. Well, that's correct. The calculator didn't make a mistake. It followed order of operations. It squared the 15 and then stuck a negative in the front. No negative number, well, no number that you square can ever equal a negative, okay? You cannot square a real number and get a negative answer. So make sure if you are using your calculator to square a negative that you enclose it in parentheses. This will read you a wrong answer every time, and notice that is there as a distractor. All right, this one is just asking us to turn factored form into standard form. Well, in other words, standard form being the trinomial ax squared plus bx plus c, we just want to FOIL these two binomials. So 5x times x would be 5x squared. 5x times negative 2, negative 10x. 2 times x is positive 2x. And then 2 times negative 2 is negative 4. When I combine my like terms, I have 5x squared, negative 10 plus 2 is negative 8x, and then subtract 4. So that puts me at choice C. All right, we are going to change this equation, which is in standard form, into vertex form. Now the process there, and you will need to demonstrate a process. You cannot use your calculator or guess and check to come up with this. You have to show your steps. But those steps are called completing the square. So what we're going to do is, let me recopy this equation first. We're going to do something very similar to what we did on number 12, I believe it was, where we chopped the b term in half. So negative 6 divided by 2 is negative 3. Then square that. So negative 3, once again, it's a negative, so I need to enclose it in parentheses. Negative 3 squared is positive 9. That means in order for this equation to represent a perfect square, this out here would need to be a 9. Right? It's like we wish it were a 9, but it's not a 9. In order to get a 9 over there, I'm going to have to add 7 more. Now, if you just add 7, you have changed the value of this equation. But if I want to add 7, and I promise that later I'll subtract that same 7, then I've really added nothing, because positive 7 minus 7 is 0. So I haven't actually changed the value of my equation, just its appearance. Now I did that so I could take this first part and rewrite it in the form of a perfect square trinomial, because now it's plus 9. However, I still have to remember there's a minus 7 that I owe out there at the end. Now, this expression, the x squared minus 6x plus 9, being a perfect square trinomial, can be written in the form of a binomial squared. To know that binomial, it's the square root of x is x. The square root of 9 could be either 3 or negative 3, but I'm going to match the sign in the middle here. So it must be minus 3, x minus 3 squared. And then don't forget, there's a minus 7 out here. Now this is in vertex form, so I can just look for my h and my k. H here is 3, and k is negative 7. So that puts my vertex at 3, negative 7. And the most recent work we've done is with factoring of trinomials. And I have suggested using that magic X, where we identify the product for which we are hunting and the sum in the top and the bottom of the X. So the product comes from our C term, that's the negative 12, and our desired sum comes from the B, negative 4. I'm looking then for two factors of negative 12 that have a sum of negative 4. Well, factors of 12 are 1 times 12, 2 times 6, and 3 times 4. I don't have that many choices. Now, in order to get a product that's negative, I have to be multiplying one positive number and one negative number. Right? Now, as I am thinking here, and I know that the sum has to be negative 4, well, the sum of a positive and a negative number, to actually find the number value of that, I really subtract. So which of these factors I listed would subtract to be 4? And that means 2 and 6. Now, since I want a sum of negative 4, I want to use the 2 as positive and the larger one, the 6, as the negative. Once I've identified the correct factors, it's just a matter of writing this as if it looked like a FOIL problem, x plus 2 times x minus 6. Number 16, exactly the same type of question. I start with our magic x. The product for which I'm looking is negative 18, and the sum is positive 3. Once again, I have a negative product, so I need one positive and one negative number. I can think through the factors of 18 there. 1 times 18, 2 times 9, or 3 times 6. Again, not many choices. And I want the set of factors that subtract, again, because the signs are different, I'm subtracting and looking for 3. Well, the factors that have a difference of 3 are 3 and 6. Since my result should be positive this time, I want the larger, the 6, to be the positive, the 3 to be negative. So my factors are x plus 6 and x minus 3.